Hello and welcome to the 28th lecture. So we're going to be talking about the definite integral. So previously we were discussing the area underneath the graph. The simplest way to introduce this is to say that the definite integral is the signed area underneath the graph. So sometimes, well, indeed often, we're going to have functions that are not necessarily non-negative, so they're going to change sign, like this. And then whatever the area of the stuff above the graph is, the stuff here in red, and the area underneath the graph, the actual definite integral is this stuff minus this stuff. Okay, so this is counted positive, and this is counted negative. Yeah? So I'm not going to say area underneath the graph anymore. I'm going to say signed area underneath the graph. And I'm going to be talking about rectangles again. And I'm not going to talk about necessarily the area of a rectangle, because the rectangle could be going downwards underneath the x-axis, and it'll be the signed area of the rectangle. Okay, but otherwise, the way we're going to try and understand this quantity here is exactly the same. In fact, we're going to do a little bit more of a general procedure. So I'm going to give you the definition of what the definite integral is now, and then I'm going to correlate it to the picture as we go along. So as I warned last lecture, it'll seem notation heavy, it'll seem complicated, but we're just describing the picture. So here we go. So given function f from a, b into the real numbers, okay, not necessarily positive. Yeah? What we're going to do to get this definite integral is we're going to cut up this ab into n little equal-sized intervals. So we're going to let delta of x be the length of each one, just as before. So it's going to be b minus a over n. Yeah? And then we're going to let xi be the first one. Sorry, x0 be the first one. And then xi plus 1 is defined to be equal to xi plus delta of x for I is equal to 0, 1, n minus 1. And just as we saw last time, that gives us, let me just put it over here, i.e. that xi is equal to x0 plus I times delta of x. Yeah? And we're going to pick sample points inside our interval. So pick xi star from this interval xi minus 1, xi for I is equal to 1, 2, all the way up to n. Okay? And then we define integral from a to b f of x to be the limit as n goes to infinity of the sum I equals 1 up to n of f acting on these sample points delta of x. Okay, so what's going on? We have our function. Okay, let's make it do something like this. Okay, this here is a, this here is b. So we're cutting it up into n pieces. So this a is x0, this is x1, this is x2, and so on. x3, x4, and so on. And then we're picking these sample points, and they can be any point inside the interval. So the first sample point, x star 1, is any point from x0 to x1. So let's say we pick this point here. Then we define the height of the first rectangle by the value of f at this point. So we create this rectangle going down here with negative area. Yeah? Then we pick the other sample point. It can be anything between x1 and x2. That's the sample point x2 star. Yeah? And maybe we take it exactly at x2, or maybe we take it exactly here. It doesn't matter. We can take any one. Let's take one over here. So we define the height of this rectangle by the value of the function on this sample point. And then the sample point from x2 to x3. If we picked it here, then it would have negative area. If we picked it here, it would have positive. We can pick either one. Doesn't matter. Let's pick one here. And then this height will be defined by this point, like this. Pick one here, like here. And then the height will be defined by this over here, like this. Okay, this is important that you go from these symbols to these pictures as quickly as, as at every step, because you can easily get lost in this kind of stuff unless you turn it into pictures straight away. Okay, this will be a meaningless thing to you unless you keep turning this into pictures. So do this all the time, right? So the final one, this is xn minus 1. I wonder if these are too small. This is xn minus 1. And this guy here is the final thing, which is xn. And then the sample point, again, anywhere in between. Say it's here. So then it defines this height. And we have a rectangle like this. Okay. So, just as we saw from the previous lectures, we let the base length of these rectangles get smaller and smaller and smaller. The sum of all these rectangles is going to look more and more like it approximates this signed area, right? So over this part here, let's just fill it out. Just fill it out just for some sort of completion. So on this part here, say we see that this stuff here, the sum of all these areas, is like the positive area here underneath the part of the graph which is above the x-axis. And the sum of this stuff here is this negative quantity, yeah, but it is minus this area here underneath this x-axis. Yeah? So this thing will indeed, in the limit, give us the signed area underneath the graph. Yeah? Okay, so the main difference is now it's not necessarily positive, and now we're allowing any sample point inside this. So this could be the left endpoint, this could be the right endpoint, or anything at all in between. Okay, cool. So you might be thinking, all right, how do I even know that this limit exists? And that's a good point. It seems rather general that we have the right to pick any of these things. But here's the theorem, which I'll explain in pictures shortly. So theorem. If f is continuous on a v, except for finitely points then this limit exists. Okay, then this limit exists. And that, I'm going to show you, isn't so surprising. So recall from the last video lecture, we had this simple function, just x squared from 0 to 1, right? Like this. And when we did the right endpoint approximation, it provided an overcount, right? Because these rectangles are always above, right? Like this. like this. So this stuff was all overcounted, right? And when we did it from the left, with the left endpoint approximation, then it was an undercount, right? So the first one is 0 height, then we have this, then we have this, then we have this, and this, okay? So we have this area. I'm filling out the wrong part. Okay, too late. And the undercount is this stuff, right? Right? So, if we have this function, this is again is x squared, so f of x equals x squared. So if you have this function, using the right endpoint, it's the most overcount we could have, right? If we have the right to pick any sample point in the interval going as far to the right, it's going to give us the maximum overcount. And if we go as far to the left as we can, it gives the maximum undercount, right? But nevertheless, as you can just see from this picture, as we let the size of the base of this rectangle, the thickness of these rectangles go down to 0, the total amount of overcount and the total amount of undercount tends down to 0, and both of these quantities will tend to the same thing. You can just see it from the picture. The total area is just this little strip and this little strip, and as we let the thickness of these rectangles go down to 0, the thickness of the area is basically proportional. It's going down to 0 too. Yeah? So that works essentially because x squared is continuous. If we had x to the 3, it would still work. If we had x to the 10, it would still work. Yeah? It'll actually work for any continuous function for the same reason. However, if there are discontinuity points, then you might think, okay, well, surely that's going to create some sort of a difference, and you're not wrong. Or you're not completely wrong, because look, take a look at what happens. If we have a discontinuity point like this, and we have the rectangle we're creating is like here, right? So if we choose our sample point to be somewhere here, then we're going to get a rectangle like this. If our sample point is like somewhere over here, and if we choose it to the right, like somewhere over here, then we're going to get a rectangle like this, which is definitely bigger, right? However, if we just have finitely many of these discontinuities, then the number of rectangles for which we're going to get a dramatically different answer is just finite, right? And again, the base of these rectangles tends down to 0, so the total area of rectangles where we get a dramatically different answer depending on our choice of sample point just becomes negligible in the limit. Though the area of all those bad rectangles, you can just forget about it. It goes down to 0. Yeah? So this thing, this limit can't fail to exist because of one discontinuity point or two discontinuity points or any finite number. That'll just be a finite number of weird rectangles that do something like this potentially, and we can forget about them. Cool. So it should seem reasonable to you that this theorem is true, that this limit will exist for any continuous function which has at most finitely many discontinuities. In fact, this limit exists for a much wider class of functions, but that's beyond the scope of this class. The functions we deal with will either be continuous or have finitely many discontinuities. This thing will always work. Okay, cool. So that is the definition. That is why we can believe it's a reasonable definition. Now we're going to do kind of a warm-up by calculating a specific, well, approximating the definite integral with a specific example. So let's take this example. Evaluate the Riemann sum. So what I didn't say, though I should have said, is that this thing is called the Riemann sum. For the function f of x equals, oops, x to the 3 minus 6x over 0 to 3 with 6 subintervals. Okay, so firstly, let me write this down, that this thing, this sum, is called a Riemann sum. So Riemann was a fantastic German mathematician, did many, many things, died at quite a young age. A Riemann sum. Okay. So let's get to work on this thing. Solution. And taking right endpoints. It also tells us what sample points it wants us to take. It wants us to take the rightmost endpoints. So our first job is to look at this interval 0 to 3 and cut it up into 6 pieces. So let's draw a little picture for that. So this is 0 to 3. We cut it up into 6 pieces. Did that not so well. Okay, so if it's 0 to 3, I'm cutting up to 6 pieces, then each one has to have length 3 over 6, which is a half, right? So the first interval is from 0 to 1 over 2, then it's from 1 over 2 to 1, then it's from 1 to 3 over 2, then from 3 over 2 to 2, then from 2 to 5 over 2. Yeah? Cool. Let's try and get some rough idea what this function is. It doesn't matter if we're too off or if it's too correct or not. We just want to have something we can somewhat reasonably draw on the diagram and not write total nonsense. So this thing for very small x, this x to the 3 is a lot smaller than this 6x, and obviously for x equals 0, this is 0, so it starts by going down. Yeah. And then we're at 3, so 3 to the 3 is 3 times 3 times 3, so it's 9 times 3, which is 27. And then 3 times 6 is 18, so it's going to be positive, so like 9 at 3. So it starts off at 0, goes down, and goes up. So something like this. It does something like this, say. Yeah? Again, it's just rough. And then if you're starting this out, then I strongly recommend that you draw the picture of the thing you're trying to do. What are we doing? We're getting an approximation of the signed area by these rectangles. We know what the sample points are. So the height of the first one is defined by this. The height of the next one is defined by this. So my picture makes it look similar, but that's just my bad picture. The height of the third one is like this. The height of the fourth one is like this. The height of the fifth one might be like this. The height of the sixth one might be like this. And then all we're doing is we're just going to add up all of these 6 rectangles. Yeah? Add up all of their assigned area. So let's do that. So what's the area of the first one? So the base is a half, right? And then its height is defined by f at a half, right? Which will be a negative quantity. So we'll have this negative signed area. So if you find this difficult, just break it down into a smaller and smaller task, right? So you know you have to have the area of all 6. Just ask yourself what's the area of the first one, then the second one, and the third one. Build it up this way. So the area of the first one is going to be like this. It's 1 over 2, and then this function f of 1 over 2, right? That's what we see. We see that is the area of the first rectangle right here. Now the area of the next one, again, the base is a half, and the height is given by f of 1, right, from here. Yeah? F of 1. And the next one, the base is a half, and the height is given by f of 3 over 2. The next one, the base is a half, the height is given by f of 2, and you see what I'm doing here. The next one, height is given by f5 over 2, and the final one, f of 3. And we have 1, 2, 3, 4, 5, 6. We have all of our 6 rectangles. Cool. All right. We can factor out this half, and now we can just put these numbers into this function and approximate it. Let's do that. So if we did that, we would have first f of a half is minus 2.875. The next thing is minus 5. The next thing is minus 5.625. The next thing is minus 4. The next thing is plus 0.625. And the next thing is plus 9. And then if we add up all these numbers, what do we get? We get minus 3.9375. Cool. So that is it, right? That is giving us exactly the thing that was being asked for us. We evaluated the Riemann sum of this function with 6 subintervals, and we took the right endpoint as our sample point. All right, not too difficult, huh? Well, not incredibly easy either, particularly if you've never seen this before. But again, you're going to be drawing the pictures, you know, because it's clear what you have to do with the pictures. It's clear what the pictures mean, right? And then all we're doing here is using our language to describe this picture. All this is just the sum of these signed areas. All right, so I'm going to raise the board, and then we're going to talk about some, or maybe I can squeeze that in right here. Let's talk about some more general properties of the definite integral. Okay, so we know that if we have some numbers ai, so given numbers ai and bi, if we consider something like this, the sum I equals 1 up to n ai plus bi, right? That's exactly the same thing as the sum 1 up to n of ai plus the sum I equals 1 up to n of bi, right? And we also know that if we take the sum from I equals 1 up to n of c times ai, we can just pull out this constant c, and it's like this. Yeah. These are basic properties of addition, right? That you guys all know well. All right, now as I told you in the last video lecture, integration is this more generalized version of addition, and you might expect that the same thing holds true for integration, and you would be right. And that is what we will do after I raise the board. So, here's a theorem. If we have continuous functions, let me just write down that fact. If we have continuous functions except finitely many points, so if f, g are continuous except for finitely many points, then we have this. We have that the integral from a to b of f of x plus g of x dx is the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Yep. And we have that the integral from a to b of c f of x dx is integral a to b dx. Okay, cool. And these are exactly the analog of those things I wrote down here just for ordinary sums. And they follow from exactly the same reason. So why? Well, if we look at this thing, integral from a to b of f of x plus g of x dx, what is this? This is the limit as n goes to infinity of the sum from I equals 1 up to n of f of x, picking our sample, acting on our sample point, plus g x acting on our sample point, multiplied by delta of x, right? And then we can break that up, and that thing is the limit as n goes to infinity of the sum I equals 1 up to n f I equals 1 up to n cool. And then both of those guys have their limit individually existing because these are functions that are continuous except for finite many points. So this is the limit of a sum where both individual sums exist as the limit. So we can break up this as the limit of the one plus the limit of the other. So it's a limit as n goes to infinity of I equals 1 to n f of xi star delta of x plus the limit as n goes to infinity equals 1 up to n g of star delta of x. And sure enough, this is what we have. Just as expected, right? Cool. So these things are definitely true. And this simplifies some of our calculations a fair bit, because our next example, well, before I go on to that, let me say that this thing follows in exactly the same way. We write out the definition, it just becomes an ordinary sum, we pull it out, pull out the constant from the limit, it just falls out in front of us. Yeah? So we're going to use that with this example. So example, calculate integral from 0 to 3 of x to the 3 minus 6x dx. Okay. And let me just be specific using Riemann sums, because plenty of you know how to do this without Riemann sums. So Riemann sums are going to be R sums from now on. Okay, solution. All right, so I'm going to break this up into these two pieces. So star equals 0 to 3, x to the 3 dx minus 6 integral 0 to 3 x dx. Yeah, for sure. Because that's just the thing we just learned here. We're pulling out the 6 and we're breaking up the sum. Yeah. So let's do one at a time. Let's do this guy. Let's do this guy first. And to do it, we're going to have to use some particular formula, because that is the nature of this particular work. And I'm going to put down a couple of formulas here that we will need to use. If you encounter this stuff in an exam, which is of course very likely, you will not need to have memorized any formulae. This is not a useful skill. The formula I'm about to put down relatively easy to prove, and the first one actually is easy to prove and known for a long, long time, and wouldn't be that hard to explain them to you, but it would just take time that we don't have. So this we're just going to accept as a fact. So this is a true fact. A cool exercise would be to try and prove that yourself. This would be harder. So I equals 3, and this turns out to be n n plus 1 over 2, everything squared. Okay, so we're going to use those facts. And let's focus on this x to the 3. So we start with and this isn't that different from what we did before with x squared, right? Yeah. So what is different is we're doing it from 0 to 3. So let's draw a picture. And it's also different, and it's a different power. It's not x squared, it's x to the 3. But let's draw a picture. So this is 0. This is 3. And we have this function which kind of grows like this. It's not really a good picture, but nevertheless, it's probably a lot higher than that. So that is what we have. And let's remind ourselves what we're doing. We're trying to find the definite integral, which in this case, since it's a positive function, is just going to be the area. And we're going to do this by cutting things up into rectangles. Okay, we're going to take n rectangles, and then we're going to pass the limit. And because we know this is an integrable function, right, it's continuous, we have no problems, we can choose any sample points that we like, and we're going to choose the right endpoint just for simplicity. Yeah? But the first thing we have to do is to find our intervals. And to do that, we have to figure out what's the length of them, right? So if we have 0 to 3, we cut it up into n equal subintervals. How long will each subinterval be? So delta of x will be 3 over n, right? Because if there are n equal subintervals, yeah, and putting them all together, they all add up to be equal to 3, yeah? That means n times this thing has to equal 3, so therefore this thing is 3 over n. Yeah? We know that the leftmost endpoint is x0 is equal to 0, yeah? And we've seen already that xi is equal to x0 plus I times delta of x. Yeah. So I'm going to write this in the most general form, and then we're going to put in specifically what we know these things are as we get along with this process. So Rn is this. It's the sum from I equals 1 up to n, where each rectangle has got its height defined by the right endpoint. So I'm going to draw it on the diagram in a second, but it's given by this, right? Because this thing is here x1, this is x2, and so on. And so the height of the first rectangle is this guy, like this. The height of the second rectangle is this guy, like this, and so on. And if you're not comfortable with that, then don't write it in the sum form. Just ask it yourself, what's the first one, what's the second one, and so on. And if you do that, you look at this picture and you say, what's the first one? Well, the base here has got length delta of x, right? So it's going to be delta of x times the height. And you see the height is given by f of x1. That's the first rectangle, that's this guy. And then what's this guy? Again, the base is delta of x, and the height is what it is at the function, what the function is at x2, so f of x2. And so on, all the way to the last guy. This thing is this thing, right? As we talked about last time, this is just notation to describe this. Cool. All right, so that's what Rn is, yeah? But now we have this general form. We put in what we know this stuff is. So x0 is 0, this thing is this, so we know that xi is actually just equal to 3i over n, right? Again, this is 0, this is I times 3 over n, so we just have 3i over n, yeah? And our function f is just x to the power 3, right? So Rn is the sum from I equals 1 up to n of, we can do this step by step if it makes you feel, I mean, it's a good idea because this might be quite new to you. So we're just going to replace the f by what we know the f is as the first step. And now let's put in what we know xi to be and what we know delta of x to be. Cool. All right. So now this is looking more and more like stuff we can figure out, right? So we can take this power and apply it to the top and bottom, and then we're going to have the sum I equals 1 up to n. 3 to the 3 is 3 times 9, which is 27. So we're going to have 27 I to the power 3. And on the bottom here, we are going to have n to the power 3. And then we have here this 3 over n as well. Yeah? Good. Now, n is just some number. It's fixed. It could be 5, it could be 12, it could be whatever. It's just a fixed number. The only thing that is moving in this expression is the I. So we can just pull out this stuff here, all this stuff to do with n. Let me just maybe multiply it out first so that it looks less like I'm doing some weird stuff. So if we multiply out all the stuff to do with n and all the numbers, so 3 times 27 is 81. Right, so we're going to have 81 over n to the 4 times I to the power 3. And then this thing, this 81 over to the power over n to the power 4 is just a fixed number now for us, yeah? Because n is just something, yeah? So we can pull it out from this sum. So we have 81 over n to the power 4, and then we have the sum I equals 1 up to n, yeah? I to the power 3. Cool. And now we use this formula which is given to us right here. So we replace this part by this explicit formula. 81 over n to the power 4, and we put this stuff in. N, the n plus 1 over 2, everything squared. Yeah. And then we can start to figure this stuff out, right? So let's multiply all that stuff. We'll square it all out. So that's kind of like n squared times n. Let's actually do it one step at a time. And then what's this? It's going to be n to the 4 plus this times this, n to the 3, but there's 2 of them, so it's 2. N to the 3 plus n squared over 4. And what's that? That is 81 over 4. And then dividing, let's break this up into individual terms. So it's going to be n to the 4 over n to the 4, which would just be 1. And then this will be 2 over n. And then this guy will be just 1 over n squared. Cool. And that is the explicit expression for Rn for this particular function. And as we know, it's going to be an overcount. And we figured out exactly what it is. Yeah? All right. Now, the actual answer is the limit of this thing as n goes to infinity. So integral from 0 to 3 of x to the 3 dx is the limit as n goes to infinity of Rn. And it is just equal, therefore, because this will drop to 0, or this will tend to 0, and this will tend to 0, so it's just equal to 81 over 4. Cool. Now, many of you have done calculus already, and you think, okay, well, I can work that out anyway. I can just find the antiderivative x to the 4 over 4 and then plug in the endpoints. 3 to the power 4 is 81, so it's going to be 81 over 4. So you can do this in 1 second, right? In one line. And as I talked about last time, you might be tempted to think that this is just a bunch of nonsense because we can do this so quickly with the tool that we haven't discussed yet that's coming up in about a week. This fundamental theorem of calculus, this beautiful discovery of Newton and Leibniz. But as I also mentioned, there is real value to doing it this way. I didn't learn it this way. I learned to do integrals with the fundamental theorem of calculus, and to be totally honest, I didn't know what I was doing. I didn't know I could do it. I could calculate all these things, but I didn't know what they meant. I didn't know the meaning of the things I was calculating. I just knew it as some rather straightforward algorithm I can apply and get the answer right. And it was only when I went to university and I learned this in a more serious way that I actually understood what was going on and what I'm actually calculating and why what I was doing was so powerful. Happily, this book, which is the most common book in the US, does it this way. It first introduces integration through this method so that we have an explicit concept of what it is, what the integral is, that it is the signed area underneath the graph, and then makes you go through this and then work with your hands to find these answers the old-fashioned way, the way pre-Newton and Leibniz, so that you really see the bones of this, and that when we introduce this tool, you'll see how powerful it is. So I offered a metaphor last time about building a house, and I want to improve the metaphor. It's so dramatic how much easier it is to do with the fundamental theorem of calculus. It's like building a house with your hammer, your saw, your nails, your cement, your blocks of wood, and your 2x4s. Building a house with just these hand tools and the materials, as opposed to living sometime in the future where you have a robot that will do this. And all you need to do is just type in your laptop the dimensions of the house, the room, the size of the room, the windows, type it in, and then the robot gets to work and does it for you. If you had such a robot, you wouldn't really understand how your house is built, right? You might be checking your phone when it's actually building your house for you, right? Whereas if you do it the long way with your own hands, using hand tools, you will know very, very well how your house is built. You will understand your house super well. That is what we're doing here. We're building it by hand. We're building these answers by hand before we introduce the powerful tools to answer this question. And there's real value for doing this. There's real value, not only for its own sake, but also to understand this thing of a Riemann sum going forward, which will be a fundamental thing for us to understand any formula in advance in calculus and towards the end of calculus 2 and for multivariable calculus. So don't reject this if you've already seen a different way to do this. This is absolutely worth doing. Okay, but we're not even finished. All we've done is found this. We've just found this part of it, and we want to find this part as well, right? So we're going to have to do that part. So I'm going to erase the board, and then we're going to continue with this problem, which we haven't finished, and then try and figure this stuff out. All right. Okay, so our task was to understand this. And we broke it up like this. And we understood that. We worked out that this thing is 81/4, and we have to do this thing. So we need integral from 0 to 3 x dx. But we can go directly to some part of where we were before, because recall we found out that for f with this interval 0 to 3, where we cut it up into n equal pieces and take the right endpoint approximation, we knew that Rn is the sum from I equals 1 up to n, f of xi delta of x, right? Where we know what these xi, this is the sum from I equals 1 up to n, f of 3i over n, 3 over n. And only at this point did we put what f actually was, which was x to the 3. Now Rf is not. X to the 3 is just x to the 1. So we can just directly put that in. So then that's the sum from I equals 1 up to n, 3i over n, 3 over n, and then that's the sum I equals 1 up to n, 9i over n squared. And again, we can pull out this 9 over n squared, and then we're going to have 9 over n squared, the sum I equals 1 up to n I. Cool. And then we can use the formula that we had before, that I erased, for the sum of I equals 1 up to n, and that is n plus 1 over 2, like this. Cool. And then it's a very similar game, right? We're going to try and understand what that is. That's 9 over 2, and we're going to have 1 over n squared plus 1, which is just 9 over 2, 1 plus 1 over n squared. And then this is an easy expression to understand the limit of. Let me write that in a bit better. So the limit as n goes to infinity of this Rn, which is the Rn for this guy, is just going to be 9 over 2. Cool. So to understand this entire expression, so let's call this thing star. Star is equal to this 81 over 4 minus 6 times this thing, 6 times 9 over 2. Okay. That turns out to be minus 27 over 4, which is equal to minus 6.75. Excellent. All right, so we can actually figure this out. We can answer this question. We can answer this question. All right, a couple things to note. We didn't have to work so hard for actually this thing, because we could have just looked at the picture. So if we just look at the picture of the function x from 0 to 3, it looks like this, right? So it's exactly half of the square with side length 3, right? It's just this, right? And the square with side length 3 has got area 9, so this thing will be 9 over 2 just for elementary reasons. So sometimes we can just figure out things by just looking at the graph. So another example is that if we look at something like this, integral from 0 to 1 of this thing, if we think for a little bit, hopefully this expression here starts to be familiar, right? And what this is it's part of a circle. So if we let y of x be this thing, then y of x squared is equal to 1 minus x squared. So x squared plus y of x squared is equal to 1. Okay, so this guy is just part of a circle, and as we go from 0 to 1, so at 0 it's 1, and 1 it's 0, so it's this. So this is a circle of radius 1, and this is just the first quarter of it. Yeah. So we know that the area of a circle of radius 1, let's call this star. So we know that the area of a circle of radius 1 is just pi, so this is just a quarter of it, so star is equal to pi over 4. Okay, so sometimes you'll see questions where it'll give you some hint, and it'll say using area or something like this, find this definite integral, and then there'll be some way to interpret this thing just as an area, and you can rather quickly get the answer in this way. Okay, next thing to learn or to note is that recognizing when you have explicit Riemann sum expressions and recognizing where they come from is a good thing to do. So, example. Suppose we have this. Express the limit as n goes to infinity of sum I equals 1 up to n of xi to the 3 plus xi sine of xi delta of x has an integral over 0 to pi. All right, so what's this doing here? So what this question is wanting us to recognize is the form of a Riemann sum, because these guys here are defining the height of each rectangle whose base is delta of x. Okay, and this is the ability to go from a Riemann sum to interpreting its integral is actually a really important skill, because when we do multivariable calculus, as I mentioned, this way of finding every single formula in multivariable calculus is to look on a small scale where it's close to linear, where you can actually calculate it, give the explicit expression for each little piece, put them in a Riemann sum, and pass to the limit. So you're going to have Riemann sums, and you have to recognize what that limit is, right? So being able to look at this and see its Riemann sum and see the limit is really important. And it isn't too hard, because we know what the nature of Riemann sum is. It's just a bunch of rectangles, right? And each rectangle is defined by each rectangle has its signed area, which is defined by its base times its signed height, right? And this part has to be its height. So this thing can only be the Riemann sum of a function where the height is defined by this guy. And since it's from 0 to pi, what this has to be is the integral from 0 to pi of the function here, x to the 3 plus x sine of x dx. Now, it's really tempting for you to think, okay, whenever I see that, I go to that. Don't learn this as an algorithm. Understand why this is true. When you see this, you've got to be thinking that this stuff is a bunch of rectangles. So I'm not even going to try and give a good graph of what this thing is. I'm just going to do just a really, 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 really bad one. So the graph is like, say, something like this, whatever. Something like this from 0 to pi. Yeah? And then when you see something like this, you've got to be thinking, okay, well, this is a bunch of rectangles like this. Okay? And this is the width of the base, and this part is the height. So if this expression is a bunch of rectangles and I'll take more and more of them, what am I getting? In the end, I'm getting the definite integral of this function. Okay? So please do not learn this as just this comes to this when you drop off this part and turn this into an integral. Please don't turn this into an algorithm. Turn this into a picture so that you see that the meaning of this as n goes to infinity is the area, or signed area more generally, underneath the graph, i.e. the definite integral. Okay, cool. So that is one of the things we have to learn. All right, we're also going to have to learn some basic properties beyond the ones I already talked about for integrals. So one of the key ones is the following. So basic properties. if we have numbers like this, a less than b less than c, and we have this integral from a to c of f of x dx, this turns out to be the integral from a to b f of x dx plus the integral from b to c f of x dx. Oh, damn it. Like this. And again, this follows from the picture. So let's draw the picture. So this is A, this is B here, and this is C. So whatever our function's doing, say it's doing something like this, say, then the signed area underneath the graph is the same as what happens when we just look at the signed area underneath the graph from A to B, so this stuff, plus the signed area underneath the graph from B to C, this stuff between these lines like this. We can just see that's true. Yeah, we can just see that's true. And therefore, written in the language of maths, that is this expression right here. Yeah. Okay, other properties. If we have f is bigger than or equal to g on the interval a to b, then the integral from a to b f of x dx is bigger than the integral of g. Okay, and this has the corollary that if we have a, oh, let's do that better. We use a already. If we have capital A is less than or equal to f of x, which is less than or equal to b, for x between a and b, then a of b c is less than the integral from a to b f of x dx, which is less than or equal to capital B of b minus a. And again, these are just pictures, right? So if we have, let's erase some space right here. If we have some graph like this of f, and so this is f, and we have a graph like this of g, okay, and we're doing this from a to b, so let's say this is a and this is b, then clearly the signed area of f, which is all of this stuff, is going to be bigger than the signed area of g. So let me turn g red. Yeah, I can just see it. And this is a special case of this, because this is this constant function just always equal to a, and then this integral of this constant function over a to b is just this, right? Yeah, it's just this rectangle of height a of length b minus a. So this integral of this constant function is this, which is less than f because of this principle, and that itself is less than the integral of the constant function of b. So this is an obviously true fact. And we can sometimes use these things to estimate integrals where we can't so easily explicitly calculate them. Okay, all right, so a lot of things to say about the definite integral. And I appreciated his notation heavy. It can seem pretty complicated, particularly if you've never seen this before. But it is not complicated. It is not complicated. It is just lengthy to write it out. It is just lengthy. The pictures are very, very clear. These are very clear pictures. The pitches, none of you will have any problem with. You will all believe me if I explain this just in pitches. Yeah? But we don't just explain in pitches. We have something, we have this language, which is very efficient, very, very powerful to allow us to describe pitches, to allow us to deduce consequences of our pitches. And that thing makes it look complicated, but it's not. If you hold on tight to the pitches, you will not have difficulty with this. You will feel comfortable with this, with enough time, with enough effort, persistence, and practice. All right, good. So that's it for today. Have a great weekend. I will see you all next week.